Hi, I'm Nicholas Conlon, a PhD student at the University of Colorado Boulder, and I'm going to talk about our work on proficiency self-assessment in human-robot teaming. Robots are being deployed for increasingly complex tasks. We can see examples of this through everyday deployments of security or delivery robots and through events such as the Dark Robotics Challenge. Though despite the best efforts of designers, engineers, and operators, misalignments between an operator's expectations of the robot and the robot's actual proficiency can lead to the robot being pushed beyond its capabilities. This is particularly true in real-world environments where there are large amounts of uncertainty and/or inexperienced operators. So what we need are ways for a robot to align or calibrate an operator's expectations with the robot's proficiency, so that the operator understands when they should and should not rely on the robot to execute the task. Prior work on robot self-assessments has looked at encoding expert knowledge about what proficient behavior is directly into the robot's memory. However, we cannot always assume the operator to be a robotics expert. Models can be learned of what competent and incompetent behavior look like and used by the robot to self-assess. However, in field robotics, we may not be able to attain examples of poor behavior. On the other hand, statistical tests let a robot analyze its existing models through sampling and simulation, and are not constrained by operator knowledge or training data. In this work, we investigated a statistical test-based proficiency measure called outcome assessment. The main idea is that before task execution, the operator communicates their task expectations to the robot. The robot does some sampling and simulation to test its models to understand its proficiency. The robot then reports that proficiency back to the operator. And now the operator can make more informed decisions with respect to the robot and the task. So we had two main research questions. First, how does reporting of the robot's proficiency self-assessment impact how operators adapt their reliance on the robot to improve task performance? And second, how does this proficiency reporting impact the operator's trust in the robot after engaging in an interaction? To answer our questions, we designed a scenario where we tasked a participant to help a robot navigate a simulated dangerous environment. There were three possible outcomes: success, where the robot navigated to its goal without falling into any craters; abort, where the participant chose to end the mission prematurely; or fail, where the robot fell into a crater and failed the task. The participant was shown the interface on the right. The top portion contained the robot's reported self-assessment. This indicated the robot's confidence in arriving at the goal, and was computed once before task execution. Below the assessment was a map, which showed the locations of the robot, the goal, craters, which could cause task failure, and debris, which could cause the robot to move erratically if driven over. The map only showed what was in the areas explored by the robot so far. Below the map was a set of control buttons. Based on the report, the participants could choose how they relied on the robot during the task. They could teleoperate the robot with manual control, let the robot drive autonomously with automatic control, or abort the task altogether at any time during execution. If they chose manual control, they could use the up, down, left, right buttons to move the robot. We had a single within subjects factor, which was the self-assessment report presence. This could be present, where the report appeared just above the map, or absent, where no report was displayed at all. Our first between subjects factor was robot reporting accuracy, and this could be informed, where the robot provided an accurate self-assessment report, or random, where the robot provided a random self-assessment report. For example, if the actual confidence was fair, random could randomly report good. Our second between subjects factor was robot performance, and this could be high, where the robot moved directly to the goal while avoiding hazards, or random, where random noise was injected into the robot's movement, which should make it more susceptible to falling into craters en route to the goal. For this talk, we will not be discussing random performance, but if you're interested, please check out our paper. To measure task performance, we computed a favorable outcome percentage, and this was the number of favorable outcomes, successes, and aborts divided by the total number of outcomes for each participant. This plot shows favorable outcome percentage on the y-axis and each condition on the x-axis. We observed that when informed reports were present, there was a significantly higher percentage of favorable outcomes compared to the absent and random condition. That is, the presence of informed reports led to improved task outcomes. To measure trust, we gave participants the multidimensional measure of trust survey after each within subject's condition. The survey uses a 7-point Likert scale, where 7 is the most trusting. And we chose to use the reliability and capability subscales because they were relevant to our example. This plot shows the trust rating on the y-axis and the conditions on the x-axis. And we observed that random robot self-assessment reports led to decreases in participant trust compared to the absent and informed conditions. That is, the presence of random robot self-assessments led to a loss in trust. In conclusion, we ran a human subject study investigating how a reported FAMSEC outcome assessment impacts participant trust and performance in a navigation task. We had 2 major findings. First, that the presence of informed robot self-assessments led to significant increases in favorable outcomes. And second, that the presence of random robot self-assessments led to significant decreases in trust. This underscores both the value of robot proficiency self-assessment and the importance of the robot's ability to reliably make that assessment. Thank you.